All right, everybody. Before we venture to thiols, which I promised we'd get to next, I have this one question, and it's a pKa that we should add to our table. Phenol, that's what this molecule is. It's a good antiseptic. Still found in some sore throat sprays. It has a very unique and unpleasant taste, but it's very effective for sore throats. The answer lies in the fact that we can talk about the unusual stability of phenoxide. Phenoxide and its unusual stability is accounted for by the fact that it has extensive resonance. First resonance form, the one I just drew, is the best. But you can generate a carbonyl and put a anion there and generate a participating resonance structure here. And it can resonate further into the ring. These two resonance structures would be virtually equal in stability. Both having C- and carbonyl. And a third structure could be generated with more resonance to an equally stable phenoxide anion resonance contributor depicted here. And there's the answer to that question. So phenol is easily deprotonated because it has a low pKa, 10. So we can use a base like hydroxide to take the H off. And I brought this up because thiols are alcohols with sulfur in the place of oxygen. And pKa is 10 for phenol. And since we're on the subject, pKa is 10 for these for a different reason. Why? If an alcohol is pKa of 17 or 18, why does a thiol have a pKa so much lower? And the answer is that the S- is more stable than the O-. Has nothing to do with resonance. Who remembers why? Answer. S- is more stable than O- because it is more polarizable. Large anions are polarizable. Large. It's a very bad looking B. Nicer B there. So that's one thing we have to know about thiols. Another thing we have to know is they're smelly. Do we need to know that? Not really. But skunks emit two major thiols. They're in the book if you want to look at them. And there's a nice discussion about how to get rid of skunk odor. Thiols are not polar. Remember, electronegativity of sulfur is the same as carbon and iodine, CSI 2.5. That's not a polar bond. So you can't wash these away. Their non-polar nature lets them penetrate into the lipid layer of your skin, and it's in there. So you're saying, oh, well, if you can take the H off, this is polar, you can wash this away, and you'd be right. But please don't be washing yourself with hydroxide solutions. That ruins your skin. I mean, you could have permanent scarring doing that. Hydroxide is a little too strong, and weaker bases don't quite do the job. So the answer is not to deprotonate the thiol to make it more water soluble so you wash it away. Oxidation of thiols is the answer. And you're not responsible for the chemicals, but you are responsible for these new functional groups. And there's a reason. One of them we've seen before. Well, thiols we just saw, so you can count that as one we've seen before. But another one that's coming up you've seen before as well. If you choose the right oxidizing agents, things like peroxides and bleach, then you can add bonds to oxygen. And then you could oxidize it further with different chemicals. The symbol O here means oxidize. And the highest oxidation of sulfur can have up to 6 bonds. Not coincidentally that sulfur's in group 6 on the periodic table. Below row 2, it can make more than a full octet. And this is one we have seen before. R was a toluene, and it was in the family of molecules called a sulfonic acid. You're responsible for knowing that's a sulfonic acid just looking at it. This one's not a sulfonic acid, and neither is this one. But all you have to know is your alphabet and your vowels. A, E, I, O, U. O is the second last one. What was right before O? I. Oh, it should be black. So know what's changing here. Sulfonic acid. What is before E? Vowel before E? Sorry, I. I gave you the answer. The vowel before I is E, sulfonic acids. And these are all more water soluble than a thiol. Hey, they got OH in them. That's definitely a polar covalent bond. So with the right oxidizing chemicals, you can make these. One of these two makes it very water soluble, and they're easily washed away. So if you want the recipe for getting rid of the skunk odor, it's in there in the textbook under thiols. And the last thing I want to talk to for about chapter 10, let's put all the sulfur stuff on this page. Another oxidation is a biochemical oxidation. If I have a protein, here's a protein strand here. And it's got one of the proteins can have this in it. And it's from one of the amino acids that used to make proteins called cysteine. And if I have another protein strand near it, what can happen is, under the right biochemical conditions, the right enzyme, you can link these two strands together and that would change their shape. And this is a disulfide, they call it a disulfide bridge. If you want to read interesting stuff about disulfide bridges in the book, it closes the chapter with a discussion of how to permanently curl your hair. It's called a perm, and sulfur's definitely involved and cystene's involved. And you can reduce this and straighten your hair or curl it up even more and then reform these to make curlier or straighter hair. So just get these sulfurs near each other where you want them, either in straight or curly hair, and then hook them up with an oxidizing step. And that actually is the end of chapter 10. We're going to do an introduction to chapter 11 in our last segment for today. That means Monday's going to be short because we all have a whole bunch of stuff to do. And we'll see you in the next segment today very shortly.